Continuing the thought on the wave length and the wave base, you know, we defined it for a good reason. So using how deep the water column is with respect to the wave form or the wavelength, we can define deep water waves, transitional waves, and shallow water waves. Okay, so if the wave base is L over 2 for this idealized wave, the depth where the orbital movement of the particles stops and you don't feel the wave motion anymore, and that happens at water depth greater than half a wavelength. So if the wave depth is greater than the wave base, then the wave is called a deep water wave because it doesn't feel the bottom, right? So the lack of orbital motion at depth is useful because you can build floating structures like this Japanese airport, a landing strip. Can you believe this is actually a floating airplane landing strip? The weight of the platform is created to go below the wave base so that it remains stable, which makes the upper part of the runway, which is above water, also very stable. This is a simple principle that's used in building this. So looking at it a little bit more carefully, all the wind generated waves in the open ocean are deep water waves because the ocean average depth is about 3 kilometers, right? Unless you are close to an island, a beach, mainland, whatever. Open ocean away from land is always deep water waves, and the wave speed is always defined as wavelength divided by the period. As we said, even though we use the term wave speed, in reality it's not a speed in the same sense as a car moving or something that you threw the ball is moving or so. It is the waveform moving, so it's technically called wave celerity or c. Okay, so here you are seeing the picture again, the wavelength, the perfect circle at the surface. The circle keeps getting smaller, and as you get to L over 2, the wave base, the waveform disappears and the wave related motion disappears. So how is this relation used? The empirical relation, we won't go through the calculations, but you can reduce it to using the acceleration of gravity relation between wavelength and wave speed. You can basically draw this curve, which is very useful for the naval officers, for example. They don't have time to do the calculation, but this chart will have helped them if they can see the wave period. Say, let's say they have a sailor on the crow's nest, which we'll see later on. It's basically the post on the ship that the sailor sits and watches on the horizon what's coming, the storm, enemy ships, an atoll, whatever storm, as I said, or whatever. And you have a good idea of the wave period in seconds, 1, 2, 3, 4, 5, and so on. This is shown up to 18 because 18-second wavelength is already quite a big wave, a long wave. Okay, so if you know the wave period, you can go on this curve and you can read the wavelength and you can read the wave speed in meter per second or feet per second. Okay, so you can see the wavelength as the period increases, wavelength increases, and as the period increases, the wave speed also increases. We'll see later on that we need to know the energy contained in the waves, so the relation with the speed dependent on wavelength and the energy dependent on the wave height. Okay, very simple relation, the empirical chart. So you just need to know there is a relation which relates the wavelength and wave speed based on the wave period, which is kind of the intrinsic property imparted by the forcing. The wind forcing kind of determines the wave period. Once you know the wave period, you can go on this chart and read off the wave speed. Okay.